Assalamualaikum, one and all. In today's episode, we talk about motional electromotive force, the EMF induced in a conducting rod which moves and cuts a uniform magnetic field. How does this type of electromagnetic induction happen? And how do we compute this motional EMF? Stick around till the end of this video. Watch and learn. Question number 1. An isolated conducting rod of length 8.00 centimeters is oriented parallel to the x-axis. It moves in the positive y direction at 3.90 meters per second in the presence of a uniform magnetic field of magnitude 0.600 Tesla that points in the negative z direction. Find letter A, the magnitude and direction of the electric field produced in the rod, and letter B, the magnitude of the motional EMF in the rod. We're given the length L of the conducting rod parallel to the positive x-axis. It moves in the positive y direction at a speed small letter v equal to 3.90 meters per second. In the presence of a uniform magnetic field, capital B equals 0.600 Tesla. That points in the negative z-axis, or that is into the page, as emphasized by the cross symbols in the figure. And our target variables are letter A, the magnitude and direction of the electric field denoted by capital E produced in the rod, and letter B, the magnitude of the motional EMF denoted by the Greek letter epsilon in the rod. Right? A positive charged particle, small q, in the rod then experiences a magnetic force Fb with magnitude F equals the absolute value of the charge small q times the speed v of the rod and times the magnetic field capital B. The direction of this force is to the left end of the rod from end B towards end A of the rod. You can check this by using the right hand slap rule. That is, extend your thumb and the rest of your fingers such that they form a 90-degree angle. The thumb representing the velocity v must be pointing upward, all right? And the other fingers representing the magnetic field capital B must be pointing into the page, all right? So your right palm, as you do the slapping, must be facing, okay, to the left end of the rod, all right? That is, the magnetic force FB is directed towards end A of the rod, all right, as represented by the red arrow in the figure. Now, this magnetic force causes the free charges in the rod to move, creating an excess of positive charge at the left end A and negative charge at the right end B. This in turn creates an electric field capital E within the rod in the direction from A towards B. all right, opposite to the magnetic force. The other red arrow pointing to the right represents the direction of the force or electrostatic force Fe. Now, the charge continues to accumulate at the ends of the rod until the electric field E becomes large and the electric force Fe equalizes the magnetic force Fb. The magnitude of the potential difference V sub AB is equal to the electric field, all right, multiplied by the length L of the rod. And um, from what I said earlier, the electric field, all right, is just equal to the product of the speed of the rod, small letter v, and uh, the magnetic field, capital B, all right, uh, with the end rod or end A of the rod at higher potential compared to point B, all right. Now, suppose the moving rod slides along a stationary U-shaped conductor, all right, forming a complete circuit. No magnetic force acts on the charges in the stationary U-shaped conductor, but the charge that was near points A and B redistributes itself along the stationary conductor, creating an electric field within it. All right? And this field establishes a current in the direction shown. All right? All right. The moving rod, we say, has become a source of EMF. Within it, charge moves from lower to higher potential, and in the remainder of the circuit, charge moves from higher to lower potential. We call this EMF, a motional EMF, represented by the Greek letter epsilon. All right? And it is equal to the product of the speed V, all right, the magnetic field, capital B, and the length of the moving rod, where in this equation, all right, V, small letter V, is the conductor speed, that is the speed of the rod. Capital L, of course, is the length of the conductor, and capital B refers to the magnitude of the uniform magnetic field. Moving on to our computations, the magnitude of the electric field, capital E, is equal to 3.90 meter per second times 0.600 Tesla, or that is equal to the electric field, capital E, has a magnitude of 2.34 Newton per Coulomb, and it is directed in the positive X direction, or that is from end A to end B of the rod, all right, opposite to the magnetic force Fb. All right, so for letter B, computing the magnitude of the motional EMF epsilon using this formula, epsilon equals speed V times uh, the magnetic field, capital B, and the length of the rod, all right, that is 3.90 meters per second times 0.600 Tesla multiplied by 0.0800 meters. So when we do our math, we get, all right, the magnitude of the motional EMF epsilon equal to 0.187 volt. Our last question, number 2. An isolated conducting rod of length 8.00 centimeters is oriented parallel to the positive x-axis at time equals 0, and A is at the origin, that is, x is equal to y and is also equal to z, all right? And the end B of the rod is at the x coordinate uh, of 8.00 centimeters. Y and z are both equal to 0. The rod moves with constant velocity expressed in terms of the x and the y component, that is, v equals 1.50 meters per second, all right? That is the horizontal component. And the vertical component, or the y component, is 2.00 meters per second, all right? In a uniform magnetic field, capital B, also given in terms of the x and z components, that is negative 0.120 Tesla, all right? This is the horizontal component, and 0.150 Tesla for the z component. Questions are, letter A, find the magnitude of the induced EMF in the rod, and letter B, which end of the rod, A or B, is at a higher potential. In problem number 2, the conducting rod has a length of 8.00 centimeters with its left end, which is denoted by A, is located at the origin of the XYZ coordinates, and the right end B, located at x equals 8.00 centimeters. The rod is moving with its uh, velocity vector given by its x component, 1.50 meters per second, and the y component, 2.00 meters per second. All right? The uniform magnetic field vector is also given by its x and z components. The x component is negative 0.120 Tesla, while the z component is 0.150 Tesla. Now, the positive z component of the magnetic field is what is represented by the dot symbols in the figure, suggesting that the positive z component of the magnetic field is directed into the reader or into the positive z axis. So just like in the discussion of problem number 1, the pre-positive charges within the rod are pushed from end A to end B by the magnetic force FB, and this results to an electric field directed from end B to end A with an electric force directed opposite to the magnetic force. Our target variable is the magnitude of the motional EMF, denoted here by epsilon. So just like in problem number 1, we use the formula for motional EMF, that is epsilon equals the speed B times the magnetic field capital B and the length of the conducting rod. But in a situation for problem number 2, the velocity vector and the magnetic field vector, as well as the length of the conducting rod, are not mutually perpendicular to one another. All right? So, we have to include here additional technique on vector product and scalar product operations. However, at this point, we can already compare which end of the rod is at a higher potential. Is it end A or is it end B of the rod? All right? Since the induced electric field within the rod pushes the positive charges from right to left, or from end B to end A, all right, we say that end B of the rod is at a higher potential compared to end A. All right, so that is already the answer to question letter B in this problem. All right, notice also that when the rod slides on a stationary U-shaped conductor, just like what is shown in the figure, the induced current in this U-shaped conductor is directed from the higher potential NB of the rod toward the lower potential end of the rod. All right. Uh, as indicated by these vector arrows representing the current around the U-shaped conductor. We say that the potential difference between NB and A, all right, represented by B's of BA, is just equal to uh, the speed V of the rod times the magnetic field capital B and the length of the rod, or that the potential difference V sub BA is exactly equal to the motional EMF. To compute the motional EMF epsilon, we apply the concept of triple scalar product, where the EMF epsilon is equal to the cross product of the velocity vector V and the magnetic field vector capital B. The result of the cross product is just multiplied by the length of the rod. And using the component method of vector multiplication, we have the given velocity vector V, all right, given in this equation where the x and the y components are used. All right. So from this velocity vector equation, we can figure out what the x component of the velocity is. All right. So that is 1.50 meters per second, while the y component is equal to 2.00 meters per second. And obviously, there is no z component of the velocity. Likewise, for the given magnetic field equation, where the x and the z components are used, all right, we can figure out that the x component of the magnetic field Bx is equal to negative 0.120 Tesla, while the y component is obviously equal to 0 and the z component is 0.150 Tesla. Earlier on, we already emphasized that the electric field, capital E, is just the speed v of the rod times the magnetic field, capital B. Hence, using the concept of vector multiplication, which says that the x component of the electric field E sub x is equal to the product of the velocity Vy and the z component of the magnetic field, capital B, minus the velocity vector along the z-axis, that is Bz, multiplied by the magnetic field, capital B, along the y-axis. Alright, so substituting, we get 2.00 meters per second, which is the value of v sub y, alright, times the z component of the magnetic field, which is 0.150 Tesla, minus the value of v sub z is equal to 0, and that of by is also equal to 0. So that means, all right, the x component of the electric field, or E sub x, is equal to 0.300 Tesla meter per second. So, with the x component of the electric field being equal to 0.300 Tesla meter per second, and using the value of the length of the conducting rod, capital L sub x, equal to 0.800 meters, all right, oriented parallel to the positive x-axis, we finally get the magnitude of the motional EMF, all right, epsilon, that is equal to 0.300 Tesla meter per second times 0.0800 meters, or that is equal to epsilon of 0.0240 volts. And earlier on, we already have the answer to question letter B, all right, where we say that the end B of the rod is at a higher potential compared to end A. So that concludes our tutorial for this topic. Till the next episode, mabuhay, mashallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.